Having reviewed convolution so far, let's try to ask the question, what is the connection between convolution and neural networks? If we want to use it on images, can't we use feed-forward neural networks? We'll try to understand this more carefully by taking the example of image classification. Let's try to understand how traditional machine learning was done earlier on computer vision. Given an image, traditional ML-based computer vision solutions for image classification would extract some what are known as handcrafted features from images. Examples being SIFT, LBP, HOG, so on and so forth. Why are they called handcrafted? Because we came up with a procedure to extract those features using some thought processes and heuristics. These were effective for quite a while, but it was a bottleneck of scaling these solutions to more datasets and scaling these solutions to more real-world images. One would, given an image, use say the raw pixels or extract edges or extract features such as SIFT and HOG. It could be many others. This was known as static feature engineering, where there was no machine learning or learning involved at all. These features were then provided to a classifier, such as a neural network, to finally give the output as, say, monument in this case. The question that we try to ask now is, instead of those handcrafted kernels for edge detection, for SIFT, or any other method, can we learn meaningful kernels or filters to solve the problem in addition to learning the weights or the parameters of the classifier? Rather, if you have an edge detector which is a Laplacian of Gaussian, which has certain weights in its kernel, or any other kernel for that matter, can we automatically learn these weights as part of the learning algorithm rather than separate these two, as the first step being a hand engineered step and the second step being a learning step? That's one of the first questions we ask. We want to go even better and ask, can we learn multiple meaningful filters or kernels in addition to learning the weights of the classifier? Why just learn one? If we are learning, we may as well learn many of them. And in addition to that, can we also learn multiple layers of meaningful kernels and filters? We now know that convolution has some nice mathematical properties, and you can have a composition of convolution operations across different layers of a neural network. So can we use that in some way to learn multiple layers of meaningful kernels or filters before we learn the weights of the classifier, or along with learning the weights of the classifier? This is possible, and this is possible by simply treating the kernel's weights or the kernel coefficients as parameters and learning them in addition to learning the weights of the final classifier. So you would have an input, you would have a convolution kernel that gives you a certain output map, which becomes your second layer. You could have another convolution kernel, which would give you an output, which would give you the feature map at the third layer. And this can now be used as input to a final layer of fully connected neurons, which give us the final output. And we can use backpropagation to update these filter coefficients at each intermediate step. This network is called a convolutional neural network. Why is that so? Because in each step, instead of taking a fully connected bipartite graph to connect the first layer and the next layer, we are going to define a set of weights which convolve on the input image and give an output feature map, and we're going to learn those weights using backpropagation. Let's try to pause here and ask one or two questions again. So learning filters seems interesting, but why not use flattened images with fully connected neural networks? Why do we want to complicate our life and learn the filters? Why can't we just take the raw pixels of the input image? Anyway, the neural network is going to learn the weights it should. Why should that be a convolution operation in between? Why can't the neural network simply take the pixels of the images as flatten them out and give them as the input to a neural network and let the layers learn whatever they should? Why cannot we do this? There are a few reasons. Let's try to evaluate them. If you take even a simple data set, such as what is known as the MNIST dataset. So this is an example of the MNIST dataset. The MNIST dataset, as we mentioned earlier, is a dataset for handwritten digits, which was used by the United States Postal Service in the 90s to automatically classify mail based on zip code recognition from images. So if you used a feed-forward neural network without convolution or without learning the filters on a dataset such as MNIST, you get fairly good performance, close to about 98%, 99% performance with a simple feed-forward network. But there are certain limitations, and let's try to analyze them. The first limitation is this method ignores spatial correlations or the structures in the images. By taking pixels and flattening all of them into a single vector, we have removed the spatial relationships that exist in different parts of the image or in different corners of the image. Pixels that are spatially separate are treated the same way as pixels that are adjacent. We seem to be losing some important information that characterizes images by doing this. That's the first concern. The second concern here is there is no obvious way for networks to learn the same features at different places in the input image. Unlike a few other machine learning problems, in images, one is expected to recognize a cat on the image, whether the cat was located on the left top or the bottom right. If we simply flattened an image into a vector, a cat on the left top would have a very different vector representation. The dimensions in which the cat exists would be very different than a flattened vector when the cat was on the bottom right. We are really not enforcing the network to learn that a cat is a cat irrespective of where it is in the image. And lastly, it can get computationally very expensive if you took an image, flattened it, and only used a fully connected feed-forward neural network. Why is that so? Let's take an example. If you had a 1 megapixel color image with 20 neurons in the first hidden layer, how many weights would you have in the first layer? Think about it. And the answer is 60 million. 1 megapixel is 10 power 6 pixels. Color image, 3 channels, so that's 3 million pixels into 20 neurons. A fully connected graph is going to end up with 60 million weights in only the first layer. You now have to add layers probably for getting better performance, and that is going to lead to an explosion in the number of weights. So how do we overcome this? We overcome this by using the idea of convolution, where we know that a filter only operates on a local neighborhood in the original image. We call these as local receptive fields. Rather, the region of the input which is used for convolution is typically known as the receptive field. So that receptive field is a local part of the image. So each hidden unit of the next layer is connected to only one local part of the input image. This serves a few purposes. Firstly, it captures spatial relationships, because if you do convolution of a filter with a patch, you are capturing the 2D spatial relationships in that region, and such relationships may not be captured by feed-forward neural networks effectively. it greatly reduces the number of parameters in the model, because now you only need to connect to a local region rather than have to have a fully connected graph where every neuron in the first layer is connected to every neuron in the second layer. So now if we take the same example, if you had a 1 megapixel color image, and let's assume now that you have a filter size of K1 cross K2 that you want to learn in that first hidden layer, how many weights would you have now? The number of weights would simply be the size of the filter itself. As we said, when you use convolution in a neural network, the filter coefficients themselves become the weights. So in this case, the number of weights would be K1 cross K2. Compare this with 60 million that we talked about for feed-forward networks on the previous slide. Secondly, convolutional neural networks introduce a concept of what is known as weight sharing. Weight sharing is you take a filter, whether you convolve it with the top right or the bottom left, you use the same values in the filter. You don't change the filter weights when you convolve with the top left and when you convolve with the bottom right, which is what you would have done if you flattened out an image and used a fully connected layer to estimate the weights in that particular layer. This has two purposes too. Firstly, as we just mentioned, it enables translation invariance of the neural network to objects in images. So as I said, whether the cat was on the left top or the bottom right, it's the same weights that are operating on them. So it would recognize a cat, be it in whichever part of the image. Secondly, it reduces the number of parameters in the model, as we just said. A third thing that CNNs also do is known as pooling. Pooling serves to condense information from the previous layer. This also serves two purposes. One, by condensing information, it aggregates information, especially minor variations are kind of averaged out to get a common output in the next layer. Secondly, pooling ends up subsampling an original image into a smaller image in the next layer. And by doing that, the next layer, when convolution is applied on that next layer, the number of convolutions you have to do reduces, which reduces the number of computations in later layers of the CNN. Let's look at each of these in more detail now. Let's start with local receptive fields. So to recap, CNNs have local receptive fields, weight sharing, and pooling. Let's review each of them in sequence. Let's start with the local receptive field. So if we used a regular feed-forward neural network, it would look something like this. So your input are these red neurons here. Your input is a handwritten digit image. Let's assume that you have, because there are 16 pixels here, you have 16 input neurons. And then the blue squares here are the neurons in intermediate layers. And finally on the output layer, you have 10 green neurons, which correspond to the 10 digits that you have. You can see here that every input neuron is connected to each hidden layer neuron here in the first hidden layer. So that's a dense connection. So, and if you now connect it to all the input pixels in the first hidden layer and so on and so forth, this becomes a very dense collection of weights, as we just mentioned. Let's contrast this with what happens if we do convolution. So if you observe here in this figure, once again, the input is 16 input neurons because that's the size of the input image. But now only pixels 1, 2, 5 and 6. So these four neurons here are the ones that contribute to the first convolution. Pixels 3 and 4 and 7 and 8 do not contribute to that first convolution. So only pixels 1, 2, 5 and 6 contribute to the computation of H11, which is the first pixel in the hidden layer. Similarly, as you move forward, you have a similar number of operations for each of your pixels in the hidden layer. How does this help? The connections now are much sparser. This sparse connectivity automatically reduces the number of weights you have to learn, as we just mentioned. Importantly, we are also taking advantage of the structure of the image. As you can see here, it is 1, 2, 5 and 6 that participate in the H11 output, and 1, 2, 5, 6 are spatially correlated as compared to 1, 2, 3, 4, 7, 8 for instance. That's another advantage of the local receptive field. One question you could ask here is, but is sparse connectivity really a good thing? Wouldn't it be better to have full connections, assuming we have infinite compute bandwidth and storage bandwidth, and let the neural network learn what it should? By having sparse connections, are we not disallowing certain pixels to interact and contribute to the next layer's output? The answer is not really. We don't lose information through this process, because as we go through the depth of such a neural network, if you look at the two highlighted neurons, X1 and X5 here, they may not interact when we consider the first hidden layer, but they may start interacting to later hidden layers indirectly, because X1 contributes to H2, X1, X2, X3 contribute to H2, and H2 and H4, where H4 gets an input from X5, contribute in the successive layer, and indirectly X1 and X5 interact over the depth of the neural network. So we really are not losing out this information as long as we have a few layers in the neural network. The second is weight sharing. Let's try to understand this with an example again. Let's say that pixels 1, 2, 5, 6 are connected through a set of weights to that first pixel hidden neuron in the first hidden layer. And similarly, the last 4 pixels, they are certain numbers, 15, 16, 11 and 12. They are connected to the last pixel of that hidden neuron. We'd like to ask the question, do we want these kernel weights to be different? Do we want them to be a different set of weights here and a different set of weights here? The answer is no. We would want that filter to respond to an object or an artifact in the image in the same way, irrespective of where it is present in the image. So this is known as translation invariance. So we want our neural network to be invariant to translation of an object in an image from one position to another position. Secondly, we can also have different kernels to capture different kind of artifacts. So it's not required that you must have one kernel for the first half, top left part, and another kernel for the bottom right part. You have the same kernel and you have another kernel to capture another kind of an artifact. Maybe one of them will capture the eye of a person, another of them will capture the nose of a person. This idea of having the same weights for all parts of your input, which comes as a default from convolution, is known as weight sharing. Clearly, this also reduces the number of parameters. Let's now try to see how a CNN looks in completion. Here is a sample CNN, convolutional neural network. Given an input, you have a convolutional layer 1, which can have many filters. So stride is 1, size of the filter f is 5 cross 5, k is equal to 6, that's the number of filters or the number of feature maps or the depth of the output in that first layer, p is equal to 0, padding is equal to 0, and the total number of parameters, what you see here, is 150. Param is 150 here. Then you have something called a pooling layer, and then a convolutional layer, then a pooling layer, and then you have what are known as FC layers or fully connected layers. Let's now try to understand what these pooling layers in between are. So you can see here that most CNNs have alternate convolution and pooling layers. At least the initial CNNs that were designed had it this way. These days there are other options, more layers that you can fit into an architecture of a CNN, which we'll revisit later in this week's lectures. Let's now try to understand what a pooling layer does. A pooling layer is a parameter-free downsampling operation. It's a subsampling or a downsampling operation, and it's parameter-free. No weights involved. You don't need to learn any weights in this particular layer. Let's see an example of one such pooling operation. So you can see here that this could be a feature map, or it could be an output of a convolution step, which is a feature map in one of the hidden layers, which is of size, say, 4 cross 4. If we now try to do what is known as max pooling with stride 2, here is how it would look. You see here that you get 1, 4, 5 and 8. You do what is known as max pooling, which means you take the maximum value from that, which is 8, and you put that here. Then you do a stride 2, which means you skip one pixel in between and then go to the next one. Once again, you take this 2 cross 2 window, the max value there is 4, and you put the 4 here. If you see down, we have the same max pool operation, same 2 cross 2 filters, but now with a stride of 1. So when you stride 1, you go to the immediate neighbor and you do not skip a step and go 2 pixels later. So in this case, you're going to have 8 as the max pool pixel here. And similarly, when you go the next step, the maximum value here again is 8, and you put 8 in the corresponding output in that layer. Let's complete this operation. So similarly, you go to the next step. When you have stride 2, you have to go to the next row. In stride 1, you now have to still complete that row, and you keep repeating this over every step. All that you have to do is in that 2 by 2 window that you're looking, no weights involved, simply take the max element and put it in that position in the next layer. As you can see, this turns out to become a subsampling operation, which means it would reduce the size of whatever image or feature map that you had here to a smaller size based on your choice of filters and choice of stride. In this example, we saw what is known as max pooling, where you take the max value in a 2 cross 2 window. But you have other kinds of pooling operations too, where you can do what is known as average pooling or L2 pooling. Average pooling is where you take the average of values in a given 2 cross 2 window. L2 pooling is where you take the L2 norm of all the weights in a given 2 cross 2 window, and so on and so forth. There are many more cousins of pooling, such as mixed pooling, which combines max and average pooling. There is spatial pyramid pooling, there is spectral pooling, so on and so forth. And we will visit some of these as we go forward through later lectures in this course. In addition to these three operations, that is local receptive fields, weight sharing, and pooling, there are also variants that one can introduce in these layers that we discussed, specifically in the convolutional layer of a convolutional neural network. Let's see a few of these variants before we close this lecture. A popular variant is known as dilated convolution, where there is a new parameter introduced known as dilation rate, which, as the name says, controls spacing between values in a kernel. So when you apply a kernel on an input image, you change the spacing in how the values are applied, are convolved of the kernel with respect to the input. So let's see an example here of a 3 cross 3 kernel, which is green in color. The blue is the input image with a dilation rate of 2. Let's see how it works. You can see now that when you convolve, you're not placing a 3 cross 3 kernel directly on a 3 cross 3 window of the input, but you're spacing things out and you're placing the 3 cross 3 kernel on that spaced out image. One could also say this is equivalent to subsampling your original image and then applying by a dilation rate and then applying the same standard convolution. Both of them turn out to be equivalent, but we're doing it in one step now. Remember, we already said sampling and interpolation can be interpreted as convolutional operations. We're just taking advantage of that now using a dilated convolution. So that's the animation of how dilated convolution looks. You can notice now that when dilation rate is 1, it becomes standard convolution. There is a subtle difference between dilated convolution and standard convolution with, say, stride 2. What is it? When you do standard convolution with, say, stride 2, the convolution is still with the original neighboring pixels in the image, just that the next convolution goes 2 pixels further. But in dilated convolution, each convolution itself is dilated and sees a larger neighborhood in the input image. Another popular variant of convolution that's used while training neural networks or CNNs is known as transpose convolution. As the name suggests, transpose convolution allows to upsample an input. What do we mean? In traditional convolution, you have an input image, you take a filter, and if you do not pad, you're going to get an output which is smaller in size. We're going to transpose that now. We're going to see if given an input image and if you convolve, can you get a bigger image without doing anything else? And that process is what is known as transpose convolution. It's sometimes also called deconvolution or upconvolution, although it is not technically deconvolution. Deconvolution means a different thing in a signal processing context, although certain articles call such an operation as deconvolution. Traditionally, we would achieve upsampling using interpolation or similar rules. We saw this in the first week of lectures, that one could take something like a tent kernel and convolve that with an image to get a high resolution image or upsample the image. We try to now ask, why should we use a tent kernel? Why cannot we learn the weights of that interpolation kernel? Let's try to see how this transpose convolution is done using an example. So you have an input. Let's see a 1D example just to keep things simple and be able to easily explain. Let's consider a 1D example which has a dimension of 4. 2301 or 230 minus 1 are the values in this input. Let's consider the kernel to also be 1D, which is 1, 2, minus 1. Now we want to find out how do we get an input which is larger than an output which is larger than the input. Let's see how we do it. We take the 1, 2, minus 1 and convolve it with the first value of the input, and that gives you 2, 4, minus 2. Then we slide 1, 2, minus 1 to the second value of the input, and we now get 3, 6, minus 3. We further slide 1, 2, minus 1 to the next location in the input, get 0, 0, 0, and finally we get minus 1, minus 2, 1. Now in each of these locations, we add up the values that we get as we convolve this filter with each location of the input. So your final output would look like 2, 4 plus 3, 7, minus 2 plus 6 plus 0, 4, minus 3 minus 1 minus 4, 0 minus 2 minus 2, and 1. This gives you the output which is now larger than the input. And you could do the same thing even in 2 dimensions to make an image larger. We will see examples of where this is used a little later in this course. Let's understand this with a visual illustration. So you can see 2 examples here. One of upsampling a 2x2 input to a 4x4 output, and another of upsampling a 2x2 input to a 5x5 output. In these images, the blue image in the middle is the 2x2 input and the green image is the output. The shaded regions show the filter and how they are applied. So you can see here that you first apply the 3x3 filter on just 1 pixel of your input, and that gives you one of the values in the output. Similarly, you move the filter on locations, and in this case the last 2 values of the filter get multiplied with 2 locations in the 2x2 input, and that gives you the value in the second location at the 4x4 output. In the 5x5 output scenario, you leave gaps in the 2 cross 2 image, and so your values are going to be slightly different here. But you see this sliding over, and as you move the 3 cross 3 filter over different parts of the 2 cross 2 image, you get different values for your for each pixel in your output image. There are other kinds of convolution that are also possible. Some of these are something that we will see in detail when we talk about their applications in different contexts, but let's briefly review them now. 3D convolution, as we already mentioned, is where you do 3D convolution and you get the output also to be a 3D volume. In the scenario that we talked about in this lecture, we did have our filter to be 3D, but our output feature map was 2D, and we made it 3D by taking many filters or many feature maps. But what if we ensure that the output is a 3D volume by the nature of convolution itself? That's 3D convolution. We also will talk about a 1 cross 1 convolution where you only convolve along the depth of a volume, and that becomes one single value in the output. So an input of W cross H cross D becomes W cross H because you convolve the entire depth along one particular pixel with a depth kernel, and you get one scalar in that particular location. You can also have grouped convolution where different filters convolve with different depths in your input. So if you had about say 100 channels in your input, one set of filters could interact with the first 10 channels, then another with the next 10 channels, so on and so forth. That is grouped convolution. We can also have separable convolution. The way we saw it in the first week, the way we could separate out convolution in 2 dimensions as convolution along 1 dimension followed by convolution along the 2nd dimension. Recall that we said that this could help reduce computations, is what we talk about here. So given an input, if you originally had a 3 cross 3 kernel to get us a 3 cross 3 output, you first have a column kernel, get an intermediate output, then have a row kernel, and then you get your final output. This is just a visualization of separable convolutions that we saw earlier in this course. We could also have what are known as depthwise separable convolution, where given an input volume, you have filters in 3 different channels for 3 different channels, and you convolve each of them individually to get 3 different feature maps, and then you run a depth convolution to compress all of them into a single feature map. Now this can be repeated for different filters to get multiple filters feature maps in this next layer. We can also look at what are known as flattened convolutions, which is very similar to separable convolutions, where you first have a filter which is along one of the dimensions, then have a filter which is along another dimension, and then have a third filter along a third dimension. In some sense, this is a combination of separable convolution and depthwise convolution. This is just a general paradigm for that. And finally, we can also have spatial and cross-channel convolutions, where we can do convolutions in parallel and then concatenate them to get an output. We will see examples of several of these types of convolutions in later lectures in this week in the context of how they are used. In conclusion of this lecture, here are your recommended readings. For an interactive illustration of convolution, please see this link. For a very nice discussion of the deconvolution operation, please see this link at distill.pub. Other good resources are chapter 9 of the deep learning book and certain notes of the CS231N course. A couple of questions for you to take away. Given a 32 cross 32 cross 3 image and 6 filters of size 5 cross 5 cross 3, what is the dimension of the output with a stride of 1 and a padding of 0? Work it out. Another question here is the max pooling layer differentiable? How do you backpropagate across it? Think about these questions at the end of this lecture. And here are some references.